Hello everyone and hello to all my young friends who are studying in intermediate and they are watching this video. My name is Salman. I am going to discuss a topic from physics and the name of the topic is surface tension. Surface tension is a very interesting phenomena and we encounter effects of surface tension in our daily lives at many places. So it's very important also. So now let's understand what is surface tension. Which surface is being talked about here? Everything has a surface: chair, table, cricket ball, ground, walls, your house. Every material object has a surface. So, which surface is being talked about here? We are referring to a free surface of a liquid. That means this free surface of liquid is under consideration, and the statement says that it behaves as a stretched membrane. Please note this word. So this is a liquid, say a snapshot of a tank or a pond. And what we are telling that the free surface of the liquid, which you can see in this snap, this behaves as a stretched membrane, means something like this. Here you can see in this uh, picture, one polythene film is being stretched. As you know, consider it as a thin film or a membrane, something like that. So what we intend to say here, that this surface of liquid, free surface of a liquid, it behaves as a stretched membrane. How is it possible? So let's learn about it. First of all, let me show you some snaps of that, pictorial examples, because uh, when in fact I read this chapter for the first time, I was also not able to understand how can a surface of liquid, free surface of a liquid, behave as a stretched membrane. But that's true. But there is some small difference also, which we'll discuss. First, we will see some pictorial examples. You can see water in a glass. Now you can see an enlarged view, water in another vessel, again an enlarged view. So enlarged view shows that there is a membrane, you can see here. But there is a difference here. What is the difference? Tension in a stretched membrane increases on stretching. As you stretch it further, the tension will increase. But the tension in liquid surface remains constant. You can't stretch it. Can you? Can you stretch a free surface of a liquid? It's not possible. So the tension remains constant. So this is the difference between the actual membrane and free surface of a liquid. It's very important. Please note it. Although I have shown you some snaps, but still if you have some doubt, you can do a very simple experiment at home and see this effect. I did it, so I'll show you. I took a glass of water and I started putting few coins here. Just see, it's a small clip. One by one I am putting coins, the water, although it is above the level of the glass, doesn't come out. Just see, as we put more and more coins, you can see the effect here. Just see the effect here. As I have put more coins and water has risen above the surface of glass, but still it doesn't come out. So the membrane can be clearly seen. This membrane is stopping it. It's not allowing the water to come. Of course, if you put more coins at one stage, the water will start coming out. But you can put many number of coins in, and the bulge of the surface will even be more. You can try out this experiment at home. Now, what are the factors affecting surface tension? We need to know that. It decreases with increase in temperature, and at a particular temperature, which is called critical temperature, it becomes zero. It is affected by the presence of impurities. If impurity is highly soluble, the surface tension increases, but if it is sparingly soluble, it decreases. It depends only upon the nature of liquid and independent of free area surface. So whether you take water in a glass or in a big, vessel, or in a swimming pool or in a pond, the surface tension will be same. It depends on the medium present on other side of the liquid. So these are the four factors. We should remember that. It's very important. So what we have read till now, we have read that surface tension of a liquid is the property by virtue of which free surface behaves as a stressed membrane. And the membrane, here it's worth noting that membrane has a tendency to acquire minimum possible area, right? So please remember this property. And I'm going to just show you examples of this. Now we'll see some examples. Shape of cotton loop in a soap film. Suppose we take a soap film on a frame and we put a cotton loop in an irregular shape here. Now what we do, we try to puncture this part of the soap film by a needle or a stick, anything. What will happen? Immediately this part, this loop acquires circular shape. Why? Can you answer? Please pause the video and think why it happens. I think some of you who know geometry correctly, or you can recall that, they will be able to answer this. We have said that the film tries to contract as much as possible. Now what will happen? Now the film is only in this remaining part of the frame except this area of this loop. So what will it do? It will try to maximize area of the loop. Now for a given parameter, the area of the circle is the greatest. Hence, this loop will take the shape of a circle. You can do this at your home. Now you can see we have put a loop which is in an irregular shape, and now I puncture this film inside this loop and it assumes a circular shape. So we can see that the film is trying to minimize its area, trying to shrink as much as possible in area. You must have noticed that we have spherical shape of liquid bubbles and small drops. Why? You can see the bubbles inside the liquid, they are all spherical in shape. And even if the drop is small, water drop, that is also spherical. Can you guess the reason? See, here also there is a film because inside is air and there is a film interface. And if you take this drop, there is a film. So the film tries to contract to minimum area. Now, what happens for a given volume? The surface area of a sphere is the minimum. That is why either it is bubble or a drop, they always take the shape of a sphere. End of the glass tube becomes rounded on heating. You must have seen these test tubes in labs. They are of this shape. You can see spherical portion here. So how do we give this kind of shape to a tube? I'll show you. See, when the end of the tube is heated, then the glass melts, liquefies, and that liquid tries to take the minimum possible area. You can see here. Now, since we are heating only end of the glass, so this portion is heated, so it will try to take spherical shape. So end of the glass becomes hemispherical, right? It takes the shape of a hemisphere. That means it assumes in that portion the shape is spherical. Small drops of mercury are spherical, whereas large drops are nearly flat. If you take out mercury on a glass plate, you will find the small drops are spherical, but the larger ones are nearly flat, not spherical. Why? What is the reason? Does the surface tension and contraction of the surface doesn't work in this larger drops? No, it's not like that. There is one more factor also. If you take mercury on a glass plate in small quantity, it assumes a spherical shape. Now, when mercury drop is poured, it tends to acquire minimum potential energy. Now, here there are two forces which are acting on this drop. One is surface tension, which tries to have minimum surface, and the other is force of gravity, which is the weight. Probably it acts from this point downwards. Now, what will happen when the drop is small? The gravity is negligible. Hence, due to surface tension, it acquires least surface area, which is nearly a sphere. But when it grows in size, gravity effect increases and it starts flattening like this. You can see. So it will try to have its potential energy as minimum. Had it been spherical, so center of mass would have been at this place. So potential energy would have increased because height is more this height. Now the center of mass is at this place only. The height is small. Had there been no gravity, then this bigger drop also would have been spherical. It's a very interesting thing. Now, flotation of needle or razor blade, or we can see insects swimming on water. Now, if you put a thin needle gently on a water surface, it keeps floating. So you can try out this experiment at home, and I'll show you how. What I'll do is I'll place a needle gently here, right? Oh, it has gone inside. Now I try to place it very slowly. Still, it goes inside. Then I do a trick. I put it on a tissue paper, and then I try to drown this tissue paper like this. And you can see the needle starts floating. Similarly, if we put a thin blade gently on water, it keeps floating like this. You can try out this at home, but do it very gently. Put it on a tissue paper and drown it. You can see it. Even you must have seen small insects like spiders, mosquitoes. They float and swim on water surface. Like this is a small spider. You can see it's floating on water surface. What is the reason? This is possible due to surface tension, because the surface of the liquid is acting as a membrane. Now, membrane is able to support these objects, whether it is needle or it is razor. See, needle and razor both are of metal, and metal has a higher density, so they should go inside water. There is no question why they should float on surface. But there is a membrane. The surface is acting as membrane, which is sufficient to take the load of these very light objects like needle, razor, and definitely these insects. But if you add some kerosene or soap, surface tension is decreased, and this insect, needle, or razor, they sink in water. That is what we do when we try to eliminate these mosquitoes which are breeding inside open water. At times you see these mosquitoes breeding there. So we put a kerosene or a soap, they will all sink inside because surface tension decreases. And then this membrane is not able to hold their load. Now let's understand how a needle floats on water surface. Now if we put a thin needle, what you have seen, on a blotting paper and keep it gently, it starts floating. So let's analyze how it happens. So this is the needle and the water surface supports it. How? Say, this is the force of surface tension which acts on this surface, which is in contact with the needle. Now what happens? The weight of the needle mg acts downwards, and there are two components of this force. One component, suppose this angle is theta, and since it's symmetrical, this will be theta. So 2t cos theta, that supports the weight, and the component in this direction 2t sin theta and t sin theta, they cancel out, right? So this is how needle floats on water. However, if you add kerosene or soap, the surface tension decreases and the surface membrane becomes a bit weak, you can say. So the needle sinks. Bubbles can be formed with soap solution and not water. What is the reason? Have you ever tried to form bubbles with only water? They can't be formed. Very small bubbles can be formed because they break at very early stage. The reason is the surface tension of soap solution is much less compared to pure water. That is why you can have bigger bubbles of soap solution compared to water. Now, here one more interesting example that soap is more effective than water in cleaning of clothes. If we see the cloth with the help of microscope, we'll find that it contains very fine pores. This is any a garment seen under microscope. The normal what you are wearing, it looks like this. It has very small fine pores, you can see here. Now, since the surface tension of soap solution is less than water, hence it enters fine holes in clothes and then bring out the dirt particles. So it is more effective in cleaning than compared to pure water. That is why you use soap. And one more interesting thing is, if soap solution is heated, what we said, the surface tension decreases on heating. So the effectivity of soap solution in cleaning is increased. So it becomes more effective in cleaning. One more interesting example is dancing of camphor on water. When small pieces of camphor are floated on pure water, they dissolve in water and the surface tension of the solution is less than that of water because it's not that soluble, sparingly soluble. And we have said that surface tension is reduced. So now if you put a small piece of camphor in water like this, divide its surface in contact with water in two parts, red one and yellow one. So red one is more than yellow one. So on red side, more camphor dissolves, and yellow side, less camphor dissolves. So red side, the surface tension is reduced. Yellow side also it is reduced, but to a lesser extent. That means the resultant is on yellow side, and hence the camphor piece is pulled on yellow side, because the surface tension here is more than that of red. Owing to this reason, it moves towards yellow side, and wherever it goes, this process continues, and camphor appear to be dancing on water like this. Now this property is used while making toys for small children. What they do is they normally attach a small piece of camphor beneath the toy, and once you put the toy on water surface, it starts dancing. Like if you put this duck, it will start moving like this. Or somewhere they put fishes, somewhere some other toys. So children are amused after seeing this. Oh, this has come to life. Now let's understand the reason behind this surface tension. What is the reason? Before understanding the reason, we have to understand the force of cohesion. What is cohesive force? Cohesive force is force of attraction between molecules of the same substance. For example, if you take some liquid in a beaker, the molecules inside attract each other, which are in the proximity, which are very close. I'll tell you how much close. But these forces of attraction are different from gravitational force, and they do not obey inverse square law. Like what is inverse square law? Suppose this is a body of mass m1 and this is a body of mass m2. There is a force of attraction between them. Suppose they are placed d distance apart. The forces of attraction is equal to g m1 m2 upon d square. So this is called inverse square law. The force of attraction between m1 and m2 obeys inverse square law. But this cohesive force, it doesn't obey inverse square law. Then what does it obey? See, if the distance between the molecule is more than 10 raised to the power minus 9 meters, so it's a pretty small, very small distance. If the distance between two molecules, say this is molecule 1 and this is molecule 2, if the distance between them, say it is d, if d is greater than 10 raised to the power minus 9 meter, so these forces are insignificant. But when the distance between them is less than 10 raised to the power minus 9 meter, then these forces increase rapidly as the distance decreases. These are cohesive force, right? Now this distance of 10 raised to the power minus 9 meters is called molecular range, and it is denoted by C. So henceforth we will use C instead of 10 raised to the power minus 9 meter. Now consider a sphere C, sphere of radius C around a molecule M in a liquid. Suppose this is a liquid and there is a molecule M. Now if you consider a sphere of radius C, Now, force of attraction on this molecule M is only due to the molecules which are inside this sphere. There are many molecules, right? Outside, we have already said when the distance is more than c, the force of attraction becomes negligible. So there is a force of attraction on this molecule M because of what all molecules are present inside this sphere. Now, since molecules inside this sphere are uniformly distributed, or you can see homogeneous, so force of attraction is equal everywhere. So these forces cancel out if the molecule is inside the liquid. Since it is pulled in all direction equally, the forces cancel out and the net force on molecule M becomes zero, right? I hope you have understood this. If you have understood this, then you will be able to easily understand the reason behind surface tension. Now, Laplace, on the basis of intermolecular cohesive force, explained the reason behind this phenomena of surface tension. Let's see his explanation. Now, you consider molecules A, B, C, D, E at different positions inside the liquid. So, say this is a liquid. You have molecule A, B, C, D, E, right? You consider the molecules at different positions. And you consider a sphere of radius C, that is molecular range, around each particle, each molecule. Okay, so we have drawn the spheres. Now, consider two layers PQ and RS, right? PQ is just the liquid surface, and parallel to this, we have taken a line passing from B, which is RS. And the distance, because you can see this distance is C. So distance between these two layers is C. Now molecule A, because it is inside the liquid, it is attracted in all direction. So net force on A is equal to 0 because it is inside. Similarly, since B is just about to touch the liquid surface, just about to touch, but this sphere is intact, so again the net force on B will also be 0. But for molecules C, D, and E, you can see this portion of the sphere is absent. So there is a resultant force downwards, which is even more for molecule D. And definitely for E, there is a full hemisphere which is cut, right? And E cannot go further until unless it goes out of the liquid. This is the maximum limit it can go, right? So whether it is molecule E, D, or C, on all these molecules, there is a net force downwards. So if we see the portion between these two layers, which I have depicted in red color, molecules between these two layers, wherever they are, whether they are here, they experience a resultant downward cohesive force. All the molecules which are between these two layers, we have only shown 3, but there will be many number of molecules. You can't count. Now, what happens if you increase the surface area? Then molecules have to come to top anywhere between these layers, and then work has to be done, because when the molecule you know goes above B position, here there is a resultant force downwards. That means if a molecule goes to this red portion, it has to do some work has to be done. This work is stored in form of potential energy. If you increase the surface area, and molecules go on the more molecules go on the surface, so they have to do work, and that work is stored in the form of potential energy. Hence, the potential energy of molecules of surface is greater than from interior. So what happens? Now, liquid surface will always try to have minimum potential energy, because that is true for every system. Suppose you take a ball to a height h. So what will you do? You will increase its potential energy. You just leave that ball, it will fall on the ground, means it will try to minimize its potential energy. Or you compress a spring. So what will happen? Once you leave it, it will again try to come to its position, because once you compress it, you will increase in its potential energy. So every system will try to have minimum potential energy. That's true for us also. If you tease your younger brother or sister, that means you are increasing their potential energy. So what they will do? They will try to reduce their potential energy, and they will definitely do some kind of pranks here or the other. I'm just saying in a lighter mood. Please don't tease your younger brothers or sister. Treat them with love and affection. Anyway, so what we have said, the liquid surface will always try to have minimum potential energy. This is possible by having minimum number of molecules in the surface. Hence, surface contracts to have a minimum possible area. And that tendency is exhibited as surface tension. I hope that you found this video interesting. Thanks for watching this video. Have a nice day.